Hello and welcome. My name is Noah Deere. Today we're doing Lesson 3 of the Vector Calculus sequence at PCC, Math 254. Today's lesson is on arc length and curvature. We are going to look at a formula for calculating the arc length and where that formula comes from. We're going to be able to take a vector valued function for a space curve and rewrite it in terms of its arc length so that the input variable is essentially going to give us, like, each unit that the input variable increases, that corresponds with 1 unit of length along the curve, which is sometimes handy to have those together. We're going to look at a formula that allows us to measure how tightly the space curve turns, so the curvature of that space curve. We're going to revisit the unit tangent vector, and then we're also going to look at the unit normal vector, which is a vector that's at a right angle to the unit tangent but points towards the inside of the way that the space curve is turning. We're then going to look at the equation of the normal plane to a curve. So the tangent vector is pointing in one way along, or it's pointing in the direction that the curve is going. The normal plane has that tangent vector as its normal vector so that the plane is at a right angle to the curve. And then we're going to look at the intersection of two surfaces. So if I have two-dimensional surfaces in 3 space and they intersect, they're going to intersect at a line, and we want to determine how long that line is as just one little application of this. All right, so let's hop in here. In response to plotting space curves, we raised the question of how long a curve is over some interval. In the case of a space curve following the path of a moving object, the question could be posed as how far the object travels over a given interval of time. It's also of interest to discuss the curvature of the space curve, how tightly it turns at different points along its path, and to have a couple of different quantitative ways of measuring this. So the first thing we're going to look at is arc length here. To determine a formula to give us the arc length of a space curve over some time interval, we will build a Riemann sum out of the lengths of higher and higher quality straight line approximations to the curve. So let's take a look here. Figure 3.1.1, arc length approximating using 2 points. So if I have this curve r of t starting, it's a little bit hard to see, but this is r of some initial time, t naught. This is r of some final time, we'll just say t sub 1, but the curve travels along here. Then this single line from r of t naught to r of t1 has a distance d equals the magnitude of the difference between these two, and that's just a pretty horrible approximation for how long this curve is, but it is an approximation. So let's do a little bit better here. We can look at figure 3.1.2, arc length approximation using 3 points. So we have the same r of t naught as our initial point. We still have the same end point, but now we're calling it r of t2 because in the middle we have r of t1 as a middle point. So we can look at the distance between r of t naught and r of t1, and then we can look at the distance between r of t1 and r of t2 for the total distance, d equaling the magnitude of the difference between r of t1 minus r of t2 plus the magnitude of the difference between r of t2 minus r of t1. We can rewrite this in summation notation. So we write the sum from I equals 1 to 2 of r of t sub I minus r of t sub I minus 1. We're taking the magnitude of the difference of each of these. So if I is 1, we're getting r of t sub 1 minus r of t sub 0. If I is 2, we're getting r of t sub 2 minus r of t sub 1. And we're going to be able to generalize this now for as many points as we want. So if we look at figure 3.1.3, we have the arc length approximation using 8 points. Arc length approximation using 8 points. We have r of t naught, and we have the distance from that to r of t1, and then r of t2, and 3, 4, 5, 6, r of t7, and r of t sub 8. So look at this. This is a slight typo. This is actually 9 points, isn't it? All right, so if we have 8 points, if we have 9 points, then there are 8 segments. So we're going to use the same kind of summation notation that we had up here, except for now we're going to do it from 1 to 8. So the first one gives us the distance between r of t naught to r of t sub 1. The second difference gives us the length of r of t sub 1 to r of t sub 2, and so on and so forth. So we're just adding all these lengths together, and that should give us a pretty decent approximation to the length of this curve. Now if we want to expand this and get an actual value, we want to let the number of straight lines between points go to infinity and make their length go to 0. So we're going to do that by looking at the change in t. So let's read here. Note then that if n equals the number of straight lines the curve is approximated by, we find that the change in t equals t sub n minus t naught over n. So this is the t sub n minus t naught. That's the total change in time from the first point. Here's my first point, t naught. Here's my last point, t sub n, for when we have n straight lines. So the total time change between here, divide that by the number of straight lines we're using, n, and that gives us the difference in time between, say, t1 and t naught, or t2 minus t1, etc., right? So then our t sub I is going to equal my initial t naught plus the change in time times I minus 1. So let's take, for example, t sub 1. This equals t naught plus change in time times 1 minus 1, which is clearly not correct because we don't want t naught. So this is actually going to be edited here if you're going along. I believe yours is already changed. Get rid of that. It's actually not going to change anything down here for how we're going to be putting everything together, but it's good to make this adjustment. But t sub 1 could be calculated this way. T sub 2 then would be t naught plus delta t times 2, so we're just adding 2 changes in time, and so on and so forth. And this we use for I is anything from 1, 2, 3, 4, etc., all the way up to whatever we've chosen for n. Now we want to have a computation for the change in r sub I, so that's r of t sub I minus 1 minus r of t sub I. And we're going to use this, which is just as we saw before. We saw the sum of I equals 1 to n of r of t sub I minus r of t sub I minus 1. We saw that up here. We do see that this is backwards, which, again, yours should be fixed by now, by the time you get the print off here. And again, this is not going to change because when we do this, we're taking the absolute value, so the difference, if it's backwards, is not going to affect the computation at all. And to get this in terms of our change in time so that we can actually turn this into an integral, we're just multiplying top and bottom by delta t. And since the change in time is positive anyways, we can plug it inside this absolute value. And to get our exact length, we take the limit as n goes to infinity, so that we're using an infinite number of infinitesimally small straight line approximations to the curve. So we get this, but this when I take this limit, that's giving us the derivative r prime of t, right, the limit as n goes to infinity of change in r over change in time. This is the definition of a derivative. So this is magnitude of r prime of t. And as n goes to infinity, my delta t goes to 0, but it goes to the infinitesimal dt. And this is going to give us the integral of this from t naught to t sub f, which is the same as t sub n. And how do we find the magnitude of the derivative? Well, the derivative, r prime of t, this equals dx dt, dy dt, dz dt as a vector. And its magnitude is going to be the square root of its components squared. So this is our formula for the arc length from some initial t to some final t value. And here again we're stating what that t sub f is. It's the same as t sub n, it's the final time. Oh, and we were supposed to have the magnitude around this vector up here. So just went ahead and put those vertical bars here. Let's go ahead and do an example. In practice, we're not going to be reworking how to get the arc length. We're just going to apply the formula. So for this function, for example 3.1.1, find the length of the curve r of t equals the vector 2 sine of t, 2 cosine of t, 5t over 0 is less than or equal to t is less than or equal to pi. So we need the derivative, first off, r prime of t equals 2 cosine of t, negative 2 sine of t, comma 5. And then we're going to apply the formula that we see up here. We are going to go ahead and say that the arc length from 0 to pi is the square root of, we're going to square each of these components now, because these are the dx dt, dy dt, and dz dt. So I square the first component and get 4 cosine squared of t plus the square of the second component is 4 sine squared of t. And the square of the third component is 25. And we want to take the square root of all of that and take the integral with respect to t, so dt here. And let's simplify the inside of this square root. This is now the integral from 0 to pi of the square root of 29. And that's because if I factor out the 4, we get 4 times cosine squared plus sine squared. Cosine squared plus sine squared is 1, so this just becomes a 4 plus 25 is 29. Again, we need our dt here. So this equals the square root of 29 times t evaluated from 0 to pi equals the square root of 29 times pi. So the length of this curve from t is 0 to t is pi is the square root of 29 times pi. Let's go ahead and give you guys a chance. Go ahead and use the formula that we see up here to find the length of the curve. R of t equals the vector 1/2 t squared, comma 1/9 quantity 6t to the 3/2, comma 3t, over the interval from t equals 1 to t equals 4. For exercise 3.1.1, I will work through the solution with you in just a few moments. And we're back. So to work through this, we first take the derivative of the curve and get r prime of t equals the vector t comma 1/6 parentheses 6t quantity to the 3/2, or to the 1/2 now, times 6, comma 3. And then I just reduced the 6's here so that we get that this equals the vector t comma square root of 6t comma 3. We then go ahead and put this into our formula where we square each of the components and add them together, put that inside the square root, essentially just using the Pythagorean theorem, the square root of the component squared. So we get the length equals the integral from 1 to 4 of the square root of t squared plus 6t plus 9 dt. The inside here, the little technique that we want to use to get through this integral is by noticing that this is a perfect square. So when we factor it, we get that this equals the integral from 1 to 4 of the square root of the quantity t plus 3 squared dt. The square root and the square cancel, and we get that this equals the integral from 1 to 4 of t plus 3 dt. Go ahead and take the antiderivative and evaluate. We get that this equals 1/2 t squared plus 3t evaluated from 1 to 4. Plug in the 4 and the 1 respectively. We get that this equals the quantity 8 plus 12 minus the quantity 1/2 plus 3, which equals 16/2. All right, hopefully we've got that all squared away. We're going to now look at reparameterization of a function from t to arc length s. Okay, so note that when we define a space curve with an input of t, we will almost always see that a single unit of t, which we often think of as time, will not correspond to a single unit length. However, it is often possible to redefine the curve in such a way where the input is the length of the curve traveled from the starting point, which we often symbolize with s. So what we're saying is essentially just we want to have our curve defined in a way so that a single unit of input change will correspond with a single unit of length. So normally if we move 1 unit of input time, that this is not going to have a unit length of 1. Say we have a unit length from here to here. So here we have S naught, and here we have S naught plus 1 unit length. So we want to redefine our function in terms of S, our length of the curve, as opposed to some variable t. So this is going to be easiest when we have linear functions. If we look at example 3.1.2, reparameterize the curve, r of t equals 2t times the unit vector I plus the quantity 1 minus 3t times the unit vector j plus the quantity 5 plus 4t times the unit vector k, with respect to arc length measured from the point where t equals 0 in the direction of increasing t. So to do this, first we need to know the arc length, s, from some starting s position, or rather from some starting time position, which will correspond to s naught here in a minute, to some final time position. This is the square root of the derivative element squared, so we want the derivative r prime of t equals 2 times the unit I vector plus -3 times the unit j vector plus 4 times the unit k vector. So I'm going to take these and plug them in as squares. So we have 4 plus 9 plus 16 dt. So this is the square root of 29 times t evaluated from t naught to t sub f, which equals the square root of 29 times t final minus the square root of 29 times t naught. Now we're just going to realize that we could do this instead of from t naught to some final time. We're going to do my t naught as 0. So when t is 0, and my t final time is just my t variable. So this just equals the square root of 29t if t naught equals 0, and our final time is just whatever our t variable is in our curve. So that allows us to note that t equals the square root of 29 over 29 times s. So I just divide this over to the other side and then go ahead and rationalize that fraction. So once I have this, I can plug it back into my curve to get that r of t equals 2 times the square root of 29 over 29 s, where I've just plugged in this for my t variable. This is in the I direction, plus 1 minus 3 root 29 over 29 in close parentheses in the j direction, plus 5 plus 4 root 29, oh, I forgot my s over here, over 29 times s in the k direction. And I just moved this up because I don't know why I put it at an angle there. And that's it. So we've now, oh, I do need to rewrite this. This is no longer r of t. This is now r of s. So if I plug in any s value, then the point we get to will be exactly whatever s is, that many units from the initial position when s is 0, which is the same thing that lines up with when t is 0. Let's go ahead and take a look at this graph. That'll kind of help us see what's going on here. Okay, so I've gone ahead and pulled that up, and what we see, my mouse, there we go. What we see is r of 0, whether the input is s or t, should give us the point 0, comma 1.5. So if I'm looking at either of, that's 3. It's r of 0 equals 0, comma 1, comma 5. We have 3 coordinates here. And so if I look at either of these equations, say I'm looking at r of t, if I plug in 0, we get 0, we get 1, we get 5. If I go here, if I plug in 0, I get 0, I get 1, and I get 5. So when t is 0 and s is 0, those correspond to the same point. Now if we're looking at r of s and we plug in 1, then we're going to get this point, and we should see that that's exactly 1 unit away from our initial point, r of 0. And then if I plug in 1 into r of t, we're going to get this point, not the same point, and this is not 1 unit away from r of 0, since this we know is 1 unit away, since we parameterized in terms of length. Okay. Yay, spinning. Let's go ahead and have you guys try this next one, exercise 3.1.2. Reparameterize the curve r of t equals the vector sine of t, comma 3t, comma cosine of t with respect to arc length measured from the point where t equals 0 in the direction of increasing t. Go ahead and give this a shot, and I will work through it in just a few moments. Go ahead and pause the video and work through this on your own. All right, and we're back. So first thing we do, we take the derivative of r of t. We get r prime of t equals the vector cosine of t, comma 3, comma negative sine of t. We take the squares of these and we plug them into our arc-length formula to get s equals the integral from 0 to t of the square root of cosine squared of t plus 9 plus sine squared of t dt. Note for my bounds I did from 0 to t instead of t naught and t final because we're setting s equals 0 to be the same thing as when t equals 0 as my starting time, and my final time is just my variable t. Now this equals the integral from 0 to t of the square root of 10, since the cosine of squared of t plus the sine squared of t equals 1 dt, and then this equals the square root of 10t once we evaluate. So we solve for t and we get t equals the square root of 10 over 10s. We plug this back in for t into my initial vector valued function to get r of s now equals the vector sine of square root of 10 over 10s, close parentheses, comma, 3 square root of 10 over 10 times s, comma, cosine of the square root of 10 over 10 times s. Great. Moving right along here, we now want to talk about curvature. If we consider a measurement for the amount of curvature on a curve, our intuition would conclude that a straight line will have curvature 0 because the tangent vector is constant, while small circles will have large curvature and large circles will have small curvature, right? So the tighter something is, the higher we want to rank that curvature, while if something is just a slight curve, that's not as curvy, so that should have a smaller number attached to it, and a straight line should have a number of 0 attached to it. The direction of the curve is not going to matter for the curvature. We just want to have a formula for the tightness of the curve without worrying about the direction of the curve. If we consider unit tangent vectors along a curve, if there is a sharp turn, the unit tangent vector changes more quickly, while if the turn is smoother or less tight, the tangent vector changes more slowly, right? So here, if I'm moving along this tight curve, the unit tangent vectors are switching direction really quickly, while here the unit tangent vectors don't change direction as quickly. Here the unit tangent vectors are the same everywhere. So we see that looking at the rate of change of the direction of the unit tangent vector is going to give us some measurement of curvature. We're going to define the curvature, lowercase Greek letter kappa, of a space curve C. Definition 3.2.1, the curvature kappa of a space curve C with capital T as the unit tangent vector and s of t as the arc length function is kappa equals the magnitude of dt with respect to s, or dt over ds. And we're going to play with this formula just a little bit. There are variations on this curvature formula. The general one, let's just talk about this real quick. So kappa equals the magnitude of dt ds, where capital T is the unit tangent function. This is saying the rate of change of the unit tangent function with respect to how far we've gone. So we don't want to do it in respect to time or with respect to t, because t could be speeding up or slowing down as we go, and we want this to just be in terms of how far we've gone, how quickly the unit tangent vector changes as we move the same amount of length. Now, dt ds, we could use a chain rule on and get that this is the same thing as the magnitude of t prime over s prime, both with respect to t now. Essentially, what we're saying is this equals the magnitude of dt vector over little dt, or over d little t over ds over ds as well, or over dt. Right, the entire proof of this we've done in a previous chapter, but this is going to, we're going to talk about the chain rule in a later chapter. For now, I want you guys to kind of take my word for it. We'll do a formal proof of this later on, but essentially this comes from the chain rule, and so if we want this with now respect to t, we can kind of think of these as two fractions where the little dt's would cancel and we would get back to our starting. So that's the hand-wavy version of why this step here is true. Now, capital T prime of t, that's going to equal r prime of t cross with r double prime of t. You see the little note on the side. The proof is left as a reading from the text, so if you open up the textbook, they do show how to get that and how we get it, that the denominator is the magnitude of r prime of t all cubed. And it's really that this equals all of this. The proof is not going to show necessarily that the numerators line up exactly and that the denominators line up exactly per se, but work through that proof out of the text if you want. here we're just going to go ahead and use this to be able to make our computations. So example 3.2.1, find the curvature of r of t equals the vector t squared comma natural log of t comma t times the natural log of t at the point 1, 0, 0. Note this will give the measure of how quickly the curve changes direction at the given point. So to do this, if I'm going to apply this last formula, since we have everything in terms of r of t, we want its derivative and its second derivative, and we're going to need a cross product and to do some cubing and do some magnitudes, all that stuff. So we're just going to apply this formula step by step. Start with finding r prime of t, I'll give myself lots of room, r prime of t equals 2t, comma 1 over t, comma, here I'm going to use product rule. I have 1 times the natural log of t plus t times 1 over t. Simplify this down. This equals the vector 2t, comma 1 over t, comma natural log of t plus 1. Okay, take the derivative one more time so that I've got the second derivative that we're going to need for the formula. R double prime of t equals vector 2, comma negative 1 over t squared. That just comes from, this is t to the negative 1. I bring the negative down, negative 1 down, make it a negative 2, and then just put it back into this form. Derivative here is just 1 over t. Now I want to take the cross product of r prime and r double prime. So I have 2t, 1 over t, and the natural log of t plus 1 crossed with 2 negative 1 over t squared and 1 over t. I write these vertically because now I can see that the first component of the cross product, I'm going to ignore the top row and use a determinant of these bottom 4 components. So 1 over t times 1 over t is 1 over t squared minus natural log of t plus 1 times negative 1 over t squared becomes a plus natural log of t over t squared plus 1 over t squared. We'll obviously be able to simplify that down here in just a second. For the middle component, I'm going to ignore the middle here. We're going to negate at the end. So 2t times 1 over t is 2, but we'll negate it to make it a negative 2. And then we do minus 2 times natural log of t plus 1, but we will negate it again to make it a plus 2 natural log of t plus 2. Again, we'll simplify that in a moment. For the last component, we ignore the bottom row. We get 2t times negative 1 over t squared is negative 2 over t minus 1 over t times 2 is 2 over t. And all of this simplifies down to the natural log of t plus 1 all over t squared, comma 2 natural log of t, comma negative 4 over t. So this is my r prime crossed with r double prime. Okay, now we need the magnitude of that, and we need the magnitude of r prime of t cubed. So let's do the magnitude. I'm actually going to write it out here. So r prime of t crossed with r double prime of t, magnitude thereof, all over magnitude of r prime of t cubed. This is my curvature. So the magnitude of the cross product here is the square root of let's make this a little bit bigger. natural log of t plus 1 quantity squared over 4 plus 4 times the natural log of t all squared plus 16 over t squared. That's just my numerator. Now our prime, we want the magnitude of this, and then we'll cube it. So we have the square root in parentheses of 4t squared plus 1 over t squared plus the quantity natural log of t plus 1 all squared, and then we take that and cube it. So this, we're not even going to worry about simplifying this. This is a pretty complicated equation, but this is going to give us our curvature, and we want specifically the curvature at the point 1, 0, 0. 1, 0, 0. So this means that we have t squared equals 1, we have the natural log of t equals 0, and we have t times the natural log of t equaling to 0. I think the middle one is most telling. This tells us that t has to equal 1. If I plug that into either of the others, we also get true statements, so this implies that this point happens when t equals 1. So I plug 1 in for t into this formula here, and I'm going to get the square root of natural log of 1 is 0 plus 1 squared is still 1 over 4. Here I plug in a 1 and I get 0. Here I plug in a 1 and I get 16. On the bottom I plug in 1 and I get square root of 4 plus 1 plus 1 all cubed. So this, let's see, 16 and a quarter by 4, 65 over square root of 6 cubed which equals the square root of 65 over 6 root 6. If we do this 3 times, we'll get a 6 root 6. And then we have the square root of 4 is 2. Bring it down, 12 root 6. And we'll rationalize this to get the square root of 360. 30 is 390 over 12 times 6 is 60, 72. Double check. This is 3 times 13 times 3 is 39 times 10. There's no perfect squares here. Alright, so that is our curvature at this point. So a lot goes into this, but this is a pretty natural definition for how to get the curvature. And so as complicated as it is, we go through this process to get our calculations. This is also something that we could program a computer to do all of this for us, as opposed to us needing to go through and do it step by step ourselves. So that could be a fun exercise for you if you wanted to set all of this up in GeoGebra, where you program in the derivative, the second derivative, automatically given a certain function, and then get it to take the cross product for you, all of those things, the magnitude thereof. The computer can do all of that and then just pop out our numbers automatically. But this one should be a little bit simpler. We just have t squared, and t cubed, no natural logs, so no product rule or anything. Hopefully this one doesn't end up as quite the headache, but go ahead and give this one a shot. I will come back and work through it with you in just a few moments. And we're back. So to calculate this, we need our prime of t, which equals the vector 1, 2t, 3t squared. We need the second derivative, which is the vector 0, 2, 6t. We take the cross product of the first and second derivatives to get the vectors 6t squared, negative 6t, 2. We take the magnitude of that cross product and we get 2 square root of 9t to the fourth plus 9t squared plus 1 after factoring out a 4 and taking its square root. We need the magnitude of r prime, which equals the square root of 1 plus 4t squared plus 9t to the fourth. Thus, our curvature kappa equals 2 square root of 9t to the fourth plus 9t squared plus 1, all over the quantity square root of 1 plus 4t squared plus 9t to the fourth, all to the third. Now the point we're talking about, 1, 1, 1, occurs when t equals 1, since if I plug 1 in for r of t equals t comma t squared comma t to the third, r of 1 equals 1, 1, 1, just like we want. So I plug 1 in to my curvature function, so kappa of 1 equals 2 square root of 19 over the square root of 14 cubed, and we can go ahead and pull out, or take 2 of the square roots of 14, make it a 14, reduce this, and rationalize to get that this equals the square root of 266 over 96. Here, I just didn't want to pull out a calculator, so I did some multiplication off to the side. All right. Getting to about the halfway point in this lecture, we have 3.3, the unit tangent and unit normal vectors. So we've actually looked at the unit tangent function already in the last lesson, and it's defined below here. Let's just read this intro. It is sometimes useful to look at a given point on a curve to be able to determine the tangent vector at that point, and then be able to adjust the tangent vector so that it has length 1. If we can do this generally for any point, we acquire what is called the unit tangent function, denoted capital T of t, which gives the direction of the curve at any point in time. It has a length of 1, so it's not going to tell us anything about velocity or anything like that. It's just going to give us the direction. Another useful function is called the unit normal function, denoted capital N of t, which gives a unit vector pointing at a right angle to the tangent vector and to the inside of the curve. That is, it points in the direction that the curve is turning. Thus, by coming up with this function, we can quickly tell the direction the curve is turning at any point in time. So the unit tangent function, by definition 3.3.1, for a vector function r is defined to be capital T of t equals r prime of t over the magnitude of r prime of t. So r prime of t gives us the direction that the curve is going, right? Because it's the rate of change of the vector itself. If I go ahead and say I have some curve here, and at this point, here is r prime of t. And then if I make it shorter, then I get the unit tangent vector, capital T of t, right? Just by dividing this by its own length. Note that this is somewhat intuitive calculation, since r prime is the direction vector of the curve at any point, and by dividing by its magnitude, we change the magnitude of this vector to be 1. Okay, now the unit normal function, definition 3.3.2. The unit normal function for a vector function r is defined to be capital N of t equals capital T prime of t divided by the magnitude of t prime of t, which gives the direction that r is turning at any point along the curve. Here again, this is somewhat intuitive, as capital T prime of t is the rate of change of the direction vector, right? So we have our direction vector, our unit tangent vector. And when I take its derivative, that's telling me how quickly we are turning, essentially. But it's with respect to time, not unit length, so it's not a good measure of curvature, but it does give us the rate of change of the tangent vector, and that the change of the tangent vector has to be going in the direction of how the curve is turning. So, hence producing a vector in the direction of the change in direction. Again, by dividing by the magnitude of capital T prime of t, we are simply changing the magnitude of this change in direction vector to be 1. let's just go ahead and do some computations, and we'll look at a graph here. Find the unit tangent and unit normal vectors, capital T of t and capital N of t, respectively, for the vector function r of t equals the vector t squared, comma, sine of t minus t cosine of t, comma, cosine of t plus t sine of t, at the point pi squared, comma, pi, comma, -1 on the curve. This is example 3.3.1. All right, so capital T of t, this equals r prime of t over the magnitude of r prime of t. So r prime of t is 2t, comma, cosine of t, minus, I need a product rule here, derivative of the first is 1 times cosine of t. It's nice, that's going to cancel for us, plus the first times the derivative of cosine is negative sine of t, comma, derivative of cosine t is negative sine of t, here plus the derivative, here again product rule, t sine of t, derivative of t is 1 times sine of t, going to get another cancellation, plus t times cosine of t. Come back for the bottom because I want to simplify this first. So this equals 2t, comma, negative t sine of t, comma, t cosine of t. And that allows me to take the magnitude a little bit easier. So the magnitude is 4t squared plus t squared sine squared of t plus t squared cosine squared of t and then here the sine squared plus cosine squared is 1, so factor out the t squared, get that, so it's just 1t squared plus 4t squared is the square root of 5t squared. If I put this all together, this is the vector. It's just the square root of 5t. It's going to cancel here. We're going to get 2 root 5 over 5, comma, here the t's will cancel. We'll get negative square root of 5 over 5 sine of t. And we'll get the t's cancel, square root of 5 over 5 cosine of t. That is my unit tangent function. I'm going to need a little bit more room to work out my unit normal function, so let's just squeeze this stuff together here. Okay, so to get my unit normal function, I'm going to say capital N of t equals capital T prime of t over the magnitude of capital T prime of t by definition. So this equals t prime is 0, comma, negative root 5 over 5 cosine of t. This one's much easier than the initial one. And the derivative of cosine is negative sine, so negative root 5 over 5 sine of t over its own magnitude. So this is the square root of 0 squared 0. This squared is 5 over 25 is 1/5 cosine squared plus 1/5 sine squared equals, so this is just 1/5 down here, square root thereof, so this is 1 over the square root of 5, and when I divide these by that, the square roots of 5 are just going to cancel out, so that's nice. We just get 0, comma, negative 1/5, my arithmetic here. This is 1 over the square root of 5. This is 1 over the square root of 5. They're just going to cancel. I'm just going to get negative cosine of t, comma, negative sine of t. Okay, so let's take a look at what this is happening. What is happening here on the graph? Okay, so here we have our curve. Show you t squared sine of t minus t cosine of t plus t sine of t is this black line here, and then we get our unit tangent function, our unit normal function. We've plugged in pi, and let's go back and just do that real quick. I'm going to get this so that it can move instead of have our single point. Here we want, if we're at this point, this pretty quickly shows us that, okay, t squared equals pi squared. So I'm guessing t should be pi. If I plug pi into the second one, sine of pi is 0, minus pi times cosine of pi is negative 1, so that's a positive pi. Yeah, that works. And then plug in a pi here, we get negative 1, plus pi times 0 is just a negative 1. So we get t equals pi, and so we want our unit tangent at pi equals 2 root 5 over 5, comma, move this, second component, plug in a pi, and we're going to get 0. Third component, I plug in a pi, I get a negative 1 for the cosine, so negative root 5 over 5. My unit normal function, when I plug in pi, we are going to get 0, comma, positive 1, comma, 0. So these should be at right angles to each other. Let's go back to the graph real quick. And so we get the same things here, and when we graph these from this point, we see that the tangent vector is going in the direction of the curve, and the normal vector is going at a right angle to that and pointing in the direction of the turn of the curve. All right. I'm not going to do it right now, but we could get this so that we get these unit vectors to move with the point using a slider. Could be a fun exercise later. Alright, let's give you guys this exercise. Find the unit tangent and unit normal vector functions, capital T of t and capital N of t, respectively, for the vector function r of t equals the vector t, comma 1/2 t squared, comma t squared. Go ahead and give this a shot, and I'll work through it momentarily. And we're back. So this one's a little obnoxious. It's not real pretty with the magnitude of the derivative of r. So I've kind of finagled it a little bit, but it's worked out just fine. So r prime is the vector 1, comma t, comma 2t, and then I just take its magnitude, which is the square root of 1 plus t squared plus 4t squared. I'm just going to go ahead and rewrite this in the form the quantity 5t squared plus 1 all to the negative 1/2 times the vector 1, comma t, comma 2t. So we could leave it, the unit tangent function, in this form. Essentially this just goes into each term and we're just leaving it outside so I don't have to write it 3 times. So this really is what we're looking at here. And to take the derivative of this and then divide by its magnitude, I totally forgot to divide by the magnitude. So I'm going to have to add that on. I'm just going to tack it on real quick, pause the video, and be right back. Alright, sorry about that. Tack this on, so I'm going to take the derivative of this using a product rule. The derivative of the first here is -1/2 parentheses 5t squared plus 1 close parentheses to the -3/2 times the derivative of the inside, which is 10t, and then times the second, 1 comma t comma 2t, plus the first, quantity 5t squared plus 1 to the -1/2 times the derivative of the second, which is 0 comma 1 comma 2. This all needs to be over the magnitude of itself to make it a unit vector, which we'll do at the end here. So I simplify the first bit. I get that this equals, big parentheses, negative 5t over the square root of 5t squared plus 1 all cubed times 1 comma t comma 2t plus 1 over the square root of 5t squared plus 1 times the vector 0 comma 1 comma 2. Close that big parentheses times 1 over the magnitude of this unit tangent vector prime. And then on the next line, go ahead, I took this, the 1 over the square root of 5t squared plus 1, multiplied it top and bottom by itself twice so that we would have a common denominator. When I do that, then I multiply that into this vector. When I multiply this by itself twice, it's just 5t squared plus 1 because it's just the square root of 5t squared plus 1 squared. So I multiply that across here and to get this vector. Let me just read this out. This equals now the vector -5t comma -5t squared comma -t squared, -10t squared, end vector, plus new vector 0 comma 5t squared plus 1 comma 10t squared plus 2 end vector, all over the square root of 5t squared plus 1 all cubed times the magnitude of the unit tangent vector prime. Okay, now the vectors on top here add together nicely. This equals the vector -5t comma 1 comma 2 all over the square root of 5t squared plus 1 quantity cubed. And then I take the magnitude of this. So this is going to be 1 times 1 over the square root of the vector component squared, 25t squared plus 1 plus 4, over the denominator squared. When I square it, the square root goes away, so I get 5t squared plus 1 cubed. And then this is nice. When I take the square root of this denominator, when I take the square root of 5t squared plus 1 all cubed, that'll cancel with the denominator that we had in the first fraction that was being multiplied. So those cancel, and then the 25t squared plus 1 plus 4 simplifies down to be 5 parentheses 5t squared plus 1 close parentheses. So our final answer is equals the vector -5t comma 1 comma 2 all over the square root of 5 times parentheses 5t squared plus 1 close parentheses. All right, so I really hope your algebra is getting better. All right, let's go ahead and move on. Equations of normal planes to a curve. So recall that the equation of a plane is given by ax plus by plus cz equals d, where the vector abc is any normal vector to the plane, a vector orthogonal to the plane, and d can then be found by substituting any point into the equation for the plane and then simplifying. Definition 3.4.1, the normal plane to a curve at a given point is the plane which contains the point in question and whose normal vector is the tangent vector to the curve at that point. So the word normal gets a little confusing. We have the normal vector, which is the vector that is going at the right angle to the tangent vector in the direction of the turn of the curve. And we have the normal vector to a plane is the vector that is at a right angle to the plane. So in both cases it's talking about right angle. We also use the word normal for normalizing something down to be a unit vector. In this case, normal means the normal plane is the plane where the entire plane is at right angles to the direction of the curve. So we're going with that right angle definition of normal in this case. So let's take a look at how this is going to come together. Example 3.4.1, find the equation of the normal plane to the curve r of t equals the vector t comma t squared comma t cubed at the point 1, 1, 1. Let's right away just note that this implies that t equals 1 to get this point. So if we're at that point, we want the tangent vector at this point to give us, so I have my curve, here's a point in question, the tangent vector here, and I'm not even going to worry about making this a unit vector in this case. Let's call this at some time naught. Then the normal plane has this tangent vector as its normal vector. So this is normal to the entire plane. So this derivative here is just going to give me my ABC for the plane. So this becomes pretty quick and easy to compute. We'll take a look at the graph here in just a moment. So r prime of t equals 1 comma 2t comma 3t squared. So in t is 1, we have r prime of 1 equals 1 comma 2 comma 3. So this is my ABC for the plane. So my plane is 1x plus 2y plus 3z equals some d value. And we get the d value by plugging the point into this equation because the point is on the plane, so it had better satisfy this equation. So we get 1 times 1 plus 2 times 1 plus 3 times 1 equals d, so d equals 6. So the equation of my plane is x plus 2y plus 3z equals 6. Let's go ahead and pull up this graph. Here we go. I'm again disappointed in myself. This is not dynamic. I can't slide this point around and have the plane go with it. I could have programmed it that way, but apparently I was going for the quick, just hardwire version of this. So here we have my curve is this line here. I'll change the color of this real quick. Here we have the tangent vector, which is 1, 2, 3, and then the normal plane we see is at a right angle to the curve at that point. It's at a right angle to the tangent of the curve at that point. Cool? And that's what we're looking at with these normal planes. So let's give you guys a shot on the next one. Scroll down here, we see exercise 3.4.1. Pause the video, work through this guy, and I will give you the solution in just a few moments. Alright, we're back. Here I look at this point, I note that the last coordinate, t, is pi over 2. So that tells us right away that t has to equal pi over 2. I get the derivative, r prime of t equals the vector negative sine of t, comma cosine of t, comma 1. I plug in the time, or the t value, pi over 2, get r prime of pi over 2 equals negative 1, comma 0, comma 1. So that's my a, b, and c for the plane. So this is negative x plus z plus equals d. Plug in the point, 0, 1, pi over 2. So we get d equals pi over 2. So the equation of the plane is negative x plus z equals pi over 2. That is that. All right. We are moving on to the last section and example of the packet. Almost done here, guys. 3.5, length of intersection of two surfaces. As a final extension to the ideas introduced in this lesson, we review how to find the curve of intersection of two surfaces, and supposing this curve is of finite length, to then determine that length. Find the length of the curve of intersection of the cylinder 4x plus y squared, 4x squared plus y squared equals 4, and the plane x plus y plus z equals 2. Here we see a graph. Let's take a look at that graph real quick. So here I've programmed in the plane and the cylinder. We see it's an elliptical cylinder, and it looks like the curve of intersection is itself an ellipse. So we will be able to find the length of this ellipse. There we go. Okay. Now, actually, I want to go from the vertical view of this. If I put this straight up and down, the equation of this ellipse, well, we've got its x radius is 2, its y radius is 1. So if I wanted to parameterize this, we could have x equals 2 cosine of theta, or 2 cosine of t, and the y is 1 sine of t. So that's how we're going to do this. The z value for this cylinder is free to roam, so that we get all z values to be whatever we want them to be. Going back here, so this here is going to have x equals 2 cosine of t, y equals just 1 sine of t, and then z is a free variable. We'll say z equals s. It's not the same as t. It can be anything we want it to be. This is a surface, so we have 2 parameters here. If I wrote this in this manner, right, we have a surface and 2 variables. This equals 2 cosine of t, sine of t, comma s. We don't need to worry about the z so much here. We can really just say let z be itself. So I'm going to take this x and y and plug them into the plane. So we have 2 cosine of t plus sine of t plus z equals 2. If I solve for z, we get z equals 2 minus 2 cosine of t minus sine of t. So the space curve, let's give it a different letter than r since I already wrote that down. Let's say q as a function of t. Well, the x parameter is 2 cosine of t. The y parameter is sine of t. And the z parameter for the curve is given by this equation now. The z for the cylinder can be anything, but the z for this curve of intersection has to be this formula, 2 minus 2 cosine of t minus sine of t. And this goes around an entire orbit when t goes from 0 to 2 pi. Right? When we had that top view, we're going to go all the way around the ellipse as t goes from 0 to 2 pi. So the length of this is going to be the integral from 0 to 2 pi of the square root of the derivative squared. So I'd better move this down here. The derivative q prime of t, which is negative 2 sine of t, cosine of t, comma, positive 2 sine of t minus cosine of t. So we square all of these, we get 4 sine squared of t plus cosine squared of t plus this has to FOIL out, so we're going to get 4 sine squared of t minus 4 sine of t cosine of t. This is screaming double angle at me, plus cosine squared of t. Move this to the left just a hair so I have room for the dt. Alright, let's hope that this all works out nicely. We have 8 sine squareds, 2 cosine squareds, minus 4 sine cosine integral. Actually, I don't think I'm going to do a double angle. I'm hoping that this factors nicely. So we have the square root of 8 sine squared of t minus 4 sine of t cosine of t plus 2 cosine squared of t dt. Now this integral, this doesn't factor in a nice way at all, so we're not going to have any way of canceling the square root. This is an elliptical integral, so the solution to this is actually, we're not going to really have an explicit way of taking the antiderivative here. So we're going to use the calculator to get an approximation. Go ahead and plug this in, and when we do, we're going to get that this is approximately, there we go, there it is, 13.5191. All right, so hopefully you followed along with that all right. I don't have an exercise for you to do. This video is getting long enough as it is, so we're going to call it right here. Thank you guys so much for watching and listening, and I will talk to you in the next lesson.